Just rocking out some Pearl Jam here. See? All right, here we go. So, you may have been looking through those notes from earlier this week and wondering what the heck a warm-up questions do at the end of the notes. Typically, I do that warm-up on the second day. This is usually a 2-day lesson. One day to introduce the new formulas, and a second day to do some warm-up questions about those means and inferences for means. So this is a warm-up that would be on a day 2. So you don't have to print this out if you don't want to. You can just work these out on a separate sheet of paper. But this is on the back of the 6.7b handout that I put on the PDF. So there's one sort of hard part about this problem. You're asked to calculate the standard error based on my bowling scores. Pretty good bowling scores. I'm up probably around a 140 now. I've been practicing in my house a lot. I throw a soccer ball. My kids are the bowling pins. I knock them over pretty readily. 5 points per kid. But these are my old scores before social distancing. Here's the hard part. You should know that new formula by now, where you have to get your standard error. You've got to take the standard deviation of the sample, the standard deviation of these 4, and divide it by the square root of your sample size. Hard part about that in this particular problem is, you're not going to want to calculate standard deviation by hand. So that's the one thing I'd say. You have to use some technology. The standard deviation, if you use StatKey or your TI 87, whatever, is around 13.2 approximately. Usually that's going to be a given in these problems, or they're going to say use technology to find that. So if I take that number and divide it by the square root of 4, because there's 4, sample size was 4, basically I'm cutting that in half. That's around 6.5, around 6.6 is the standard error. I recommend you try doing part B, part C, and part D, and come back in a minute. Pause this thing if you can. So hopefully by now you're pretty comfortable knowing that the distribution is usually going to be centered at whatever the sample value is. The sample average for my bowling is around 120, 120.5 precisely. So it'll be centered somewhere between 120 and 121, somewhere around there. Should make sense. That's not a new topic. We've been doing things with that. Don't forget my bar on there, my X bar. Would the distribution be normal? That's sort of a very small sample size, so it may be kind of hard to see, but none of those appear to be outliers. I didn't like bowl a 10 or bowl a 300 in one of those bowling games. So you can it's sort of safe to assume probably going to be a normal distribution. There don't appear to be any extreme values to throw things off. And then we get to part D, which is about writing a confidence interval. Now, to write the confidence interval, you need the table. We're going to spend a whole focus on this in the next unit, but if you remember back to earlier in the year, we've been, you take the sample statistic and you add or subtract the margin of error to get your confidence interval. Here's what's kind of new. Typically, the margin of error is your standard error times whatever level of confidence you want based on Z or Z star. We're not using Z anymore, though. For means, we can't use Z because the sample size is way too small. We've got to use T. And of course, if you remember, T comes from that new table that I gave you a PDF of. And I don't have to look very far down the table on here because I only have 3 degrees of freedom because my sample size was 4. Now, just to show you how to use this table, this is a preview of the next section. If I want to be 90% confident, that means there's going to be 5% on each end of the confidence interval. So hopefully I did this right. I'm going to go to my 5% column. 5% below and 5% above. See if I did that right. I did. And I go down to 3 degrees of freedom and I'll see 2.353. That acts as my Z star, which we'll actually call T on here. If I multiply that by my standard error, that'll give me the margin of error. We're already into the sample is around 120. So I can calculate my confidence interval from that. Now, kind of a coincidence, maybe due to the rounding on here. Hey, Tris, can you turn that down and be quiet, please? Kind of a coincidence that these numbers happen to be the high and the lows of my actual bowling rounds. Just a coincidence. That will not always happen, so don't assume that's going to happen. So, comes to actually writing the confidence interval, you can be pretty sure that my bowling is going to be between a 105 and a 136. Like I said, just a coincidence that the high and low exactly matched the original values on here. That usually does not occur. Hopefully that makes sense. Second question on that document for part B is which of these distributions are appropriate. Try this one. I'm going to come back because this video gets more than 5 minutes. Or pause it and try these on your own. So, because I'm running out of time on here before this video gets too long, I'm going to answer this kind of quickly. If you look at these three, I'd probably say which one's the most appropriate in class to use a t-distribution, and hopefully you'd say probably this one because it's the closest thing to normal. If you count dots, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, it's only got 26 dots, which doesn't make our magic number of 30, but 25 dots, I guess. But because it's approximately normal, we're okay. We can do some bootstrapping on this and make our inferences. The fuel economy one, however, we're in big trouble. We've got an extreme down here and an extreme down here. It would not be wise to try and use this for a t-distribution. Weird things would be happening on here. And then the last one down at the bottom here, tons of samples. We're way over n equals 30. But I would say you still do not want to use a t-distribution because of this huge skew right here. For whatever reason, the test that I gave out, everyone's getting 100% on it. You should not use a t-distribution because it's not going to look anything like a normal curve if you bootstrap this, because this is so much more likely to occur. So those are sort of the three rules of thumb. I mentioned the other one. Here's sort of the visual example of those. Hopefully that makes sense.